Hello everybody, I'm Yee Feng. My Matric number is 207277. So today I'll be explaining about first and second law of thermodynamics and applications. The first law of thermodynamics states that a system is a region of space that includes the atom molecule that we are studying. Everything else is called as surroundings. The amount of energy of a system plus the amount of energy of surrounding is constant. Energy can't be created nor destroyed. Energy can only be transformed from one form to another form. As you can see in my slide, the last sentence state that written as E of a system plus E of a surrounding equals E of universe, and then E of a universe equals to constant, which is constant. Yes, as you can see in my slide, there's a coffee, right? So we can just imagine that the coffee as a system and the air surrounding it will be the surroundings. So the heat can be transferred from a coffee into the air or from the air into the coffee. So the heat can be transferred from the system to the surroundings and vice versa. And also energy can be transformed from one form to another. Let's say that we eat the food, right? The food contains chemical energy. The food will be digested by our system, and then it will be changed to heat energy for our muscles to relax, contract, so that we can create the movement to carry out our daily life. So from a chemical energy to heat energy is a transfer of energy. So in thermodynamics, we consider the energy enter the system to be positive, while the energy exit the system to be negative, as it's a waste of energy, while the work done into the system is negative, but work done by the system, which is positive, which is the work out. So in this slide, you will see the open and closed system. Okay, so the first diagram is state an open system. Why is open system? As there is contact with the surroundings. There is an in contact of a system with the surroundings. It's not a closed system. And for the second one, it's a closed system, which means that it doesn't have contact with the surroundings. So there won't be a change of mass inside the system, but however, there will still be the change of heat. The heat can transfer in and out of the system. But however, for third one, it is like a well insulated system, right? So it's also so-called adiabatic system. In this system, in the well-insulated system or the adiabatic system, there won't be transfer of heat in and out of the system, and also there's no change of mass in the system. So in thermodynamics, there are several conditions, which is the adiabatic, isobaric, isothermal, and isochoric. Adiabatic means that there's no heat transfer in and out of the system. For isobaric means that the system is always having constant pressure. For isothermal means that the temperature of a system is always the same. For isochoric or isovolumetric or isometric means that the volume of a system is always the same. So in the first law, we will be having a general equation for closed system is Q minus W equals to change in internal energy. The U is the internal energy plus potential energy plus change in kinetic energy. For open system, it will be Q minus W equals to change in enthalpy. The H is enthalpy plus change in potential energy plus change in kinetic energy. So how to apply first law? So the purpose of first law is to determine, we can use the first law to determine any variable in the equations Q, W, internal energy, potential energy, kinetic energy, or the enthalpy. So let's see. Let us look at the examples. So in the examples one, the steam of 3 megapascal and 40 degrees Celsius enter adiabatic nozzle steadily with velocity of 40 meters per second, then leave the nozzle at 2.5 megapascal and 30 meters per second. Determine the X temperature. So the first step is draw a diagram and then state the condition in and out. So the inlet is 3 megapascal, 400 degrees Celsius, 40 meters per second, and also is steam. The outlet condition will be 2.5 megapascal, 30 meters per second. So since it's an open system, right, as there's inlet and outlet, so we just make it to be Q minus W equals to H2 minus H1, which is a change in enthalpy plus change in velocity. It will be V2 squared minus V1 squared over 2 plus change in potential energy, which is G bracket Z2 minus Z1 bracket. So as in the question is that it's adiabatic conditions, so the Q will be 0 and there's no work done, so W is 0, and also there's no change in elevations, so the Z2 minus Z1 will be 0. So the equation will be 0 equals to H2 minus H1 plus V2 squared minus V1 squared divided by 2. So we found that the H1 enthalpy 1 of the steam at that condition is 3231.7 kilojoule per kg. So we just use a mathematical method, and then we can find out that H2 equal to 351.7 kilojoule per kg. So by using steam table, we can just find out that the temperature of that condition is 553.08 degrees Celsius. So this is how we use the first law of thermodynamics to find out the condition of the system. So a system needs first and second law of thermodynamics to be constructed. Why? So what is the limitation of first law? The first law, okay, so we will use the example of coffee again. So you see in this coffee, right? Okay, so in this coffee, it only have two conditions. First thing is the coffee is hot. So the heat energy transfer from the coffee into the surroundings. Or the second option is the coffee is colder than the surrounding air, so the heat from the surrounding air will be transferred into the coffee. But however, let us make a hypothesis. Okay, the hotter coffee, there's a hotter coffee, right, and the surrounding air is colder. But however, the heat transfer from colder environment, which is surrounding air, into the hotter system, which is the coffee. It seems awkward, right? But however, it doesn't violate the first law of thermodynamics. But however, we all know that it's impossible to happen. Energy will transfer from high place of high amount to place of lower amount. So that's why we need the second law of thermodynamics. Second law of thermodynamics will state the direction of the energy flow. So second law of thermodynamics explained in terms of entropy. So entropy is a quantity that measures the randomness of a universe. The second law states that the randomness of a universe is always increased. The enthalpy of a system can decrease as long as the entropy of a surrounding is increased by a greater amount. For the second statement, you will just understand by after I explain about the conditions with examples. So as you can see, in this condition, there are two diagrams. The first diagram is there's a black line. There's some obstacles in between the two columns, and for the right diagram, there is no obstacle in between the two columns. So in the first diagram, right, there will be in the first diagram of the left column, there are 6 molecules. So let us imagine that each molecule possesses the same amount of energy. But however, due to the presence of obstacles, it can't be transferred it can move towards the right column. So which means there's little amount of movement, so there's less entropy. But however, when the obstacle is removed, the molecule will transfer to the right side. So this states that energy tend to be dispersed, to be random, which means to be dispersed, and which means to be equal. So in the final condition will be each side will have 3 molecules of having the same energy, and the energy in between the left column and right column will be balanced. So this one we call as it has a higher entropy as the energy is randomized. So the second law of thermodynamics also can be applied in physical and to explain the physical and biochemical process. Okay, so for the condition, you see in the slide there's non-polar and non-polar molecule, right? And the blue dot, the blue circle is a water molecule. Just imagine a beaker of water. Okay, so before I place the non-polar molecule, the water molecule are moving freely and then forming a hydrogen bond with the surrounding water molecule, right? But however, after I put 2 non-polar molecules into the beaker of water, there will be water molecules surrounding the non-polar molecule. So this condition, it restricts the presence of non-polar molecule, restrict the movement of the hydrogen molecule, as there will always be hydrogen molecules surrounding the non-polar molecule, right? Not hydrogen molecule, water molecules surrounding the non-polar molecule, right? So this restricts the movement, and then it results in lower entropy. So which means that this condition is not favorable. So that's why there will be hydrophobic effect in which the two non-polar molecule they will try to stick to each other, as by sticking to each other there will be less water molecules sticking around them. As you can see in the first diagram, in each non-polar molecule, there are 6 water molecules surrounding them. So total is 12 more water molecules. But however, after sticking together, there are only 8 water molecules. So which means that there are more water molecules released to form hydrogen bond with other water molecule, and there are more movement of water molecule. So which means that this result in a higher entropy. So and this law and this every process must obey this law. Every chemical process must obey this law in order to have chemical reactions. So for the second law of thermodynamics, right, it will also produce about two statements, which is Kelvin-Planck statement and also Clausius statement. In Kelvin-Planck statement, it states that it's impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. It seems complicated, right? But never mind, let me explain it. So in the diagram, is explained about the Kelvin-Planck statement. So just now it stated that it's impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. It states that it's impossible. Let's say that if the QH, right, let's say that the thermal energy reservoir it supplies the 100 kilojoule to the heat engine. It's impossible for the heat engine to convert all the 100 kilojoule of heat of energy to become work done. There must be some energy. There must be some energy released to the another surrounding, to the second reservoir with the atmosphere. So which means that this states that it's impossible for any engines or device to have 100% efficiency. So this may result in the energy wasted as normally the QL, which is the 50 kilojoule, the QL released to the energy released to the surrounding is not what we want, but however it has no choice. It is the law to obey. So for the second one, statement is Clausius statement. The Clausius statement states that it's impossible to construct a device that operate in a cycle and produce no effect other than the transfer of heat from lower temperature body to a higher temperature body. In this statement, it states that the energy will always transfer from the place of high amount to place of low amount. By reading this statement, you may just define me and say that the refrigerator work like this. The heat is transferred from colder environment to hotter environment. But however, do you understand the working principle of refrigerator? So in refrigerator, right, as you can see, there will be evaporator, compressor, condenser, and expansion valve. Okay, so the evaporator is inside the evaporator. In the side of evaporator, the heat inside the refrigerator area of a refrigerator is transferred to the evaporator. The refrigerant inside this loop, it will have a lower temperature than the refrigerator area. So the heat is transferred from a higher temperature area to a low pressure temperature area. So it will be transferred to here, and then the refrigerant will be compressed. As we know that the pressure is directly proportional to the heat, right? With an increase of pressure, there will be increase of heat also. So in this loop, right, it will be a high pressure gas, and then there will be and then the refrigerant will reach the condenser. So part of the heat will be reduced here, will be reduced to the atmosphere, and the outside air, and then it will just flow back to the expansion valve. So it's still high pressure liquid, right? After reaching the expansion valve, it reduces the pressure, and by reducing the pressure, we also reduce the temperature. So in here, it will become a low pressure liquid again. So low pressure liquid again, also lower temperature than the refrigerated area. So again, the temperature inside the heat inside the refrigerated area, which has higher heat, will be transferred into the evaporator, refrigerant, and then become a low pressure gas, and then will send back to compression again. So this is a loop of the look of the refrigerator. So it states that the energy of the, so the second statement, the closest statement also state that the energy will always transfer from high amount, place of high amount to a place of low amount. So it's impossible for energy to transfer from low amount to high amount. So thank you. This is the end of my presentations.